good afternoon, and happy Friday to everybody tuning in on our Facebook and YouTube sites. My name is Josh. I am part of the Morrison Planetarium team at the California Academy of Sciences. We are here for another one of our Friday Cosmic Conversations, and I am overjoyed to be joined by the one and only Ella Holme, a PhD candidate from Stony Brook University, who's going to tell us some really cool stuff about Earth and our next-door neighbor, Mars. So, Ella, how are you doing?
I'm great. How are you doing, Josh?
It is a fantastic and strangely sunny day out on the West Coast, so I think we're all really enjoying that, trying to soak up as many photons as we can. So we are talking today about Earth and Earth analogs and some of the exciting stuff we can learn. You mentioned on our practice not only about what Earth can teach us about other planets, but what other planets can actually teach us about Earth. I thought that was really cool.
Cool. Do you want me to elaborate on that a little bit?
Absolutely, if you'd be willing to.
So mostly what I'm interested in is how we can use Earth to study planets like Mars, but also how Mars can actually inform us about the history of Earth. Because we think that at some point in the solar system's past, Earth and Mars were very similar planets. And Earth obviously went in one direction and Mars went in the other. So a lot of what I'm interested in is what happened to Mars. Why isn't it the same as Earth is today? And one of the really cool things about studying Mars is that unlike Earth, Mars doesn't have active plate tectonics. So all of the rock that is currently on the Martian surface has been there for a really, really long time. And it doesn't get recycled in the same way that it does on Earth. So we can look really deep into the rock record of Mars and understand things about its history that we can't see on Earth anymore, because either the rock has been recycled back into the crust or because it's been so overprinted by metamorphic processes or burial diagenetic processes that we can't learn anything about the primary history of the rock. But on Mars, we don't have that issue. So, and we're going to talk a bit later about the Perseverance rover mission and how we're going to be bringing samples back. And I can talk a little bit more then once we've had some more context about why that's so exciting to all Martian scientists, but also to me personally.
An exciting thing to get your hands on for sure. So we're actually going to be visiting Earth and Mars today using our OpenSpace software, which is a really cool planetarium program, one we actually use in our dome. And the really awesome part is it's one you can use at home. If you're interested, check out the OpenSpaceProject.com to download it. Fly around. You can even explore some of the exact same places we are going to be visiting today. I'm flying around in the brand new version 0.16. And if you download the brand new version, you can see pretty much the exact same stuff. We're not doing anything too fancy other than, flying between planets, which is always kind of a cool thing to do. So we are looking down at planet Earth in photos that were taken, I believe, yesterday. And in this view, you can actually see some of the weather we're having on the West Coast. Beautiful and sterling right out there. Always a cool thing to see the weather from yesterday recorded. But we're going to go visit some place that is, famous for being sort of inhospitable, not at all clement, but still here in California. Can you tell us about Death Valley, Ella, and why it's such an interesting Mars-focused place?
Sure. So the reason that we're going to Death Valley first is because Death Valley is one of the most famous areas that we've used as a Martian analog. And one of the main reasons for that is because if you look around at the scenery here, you can see that it is pretty barren. There's not a lot of vegetation. Of course, famously in Death Valley, there's very little rainfall. So we have a very dry climate that is not super hospitable to any large forms of life. And there are also a lot of extreme environments in Death Valley, such as the Badwater Salt Flat and the Ubehebe Crater. And a lot of the reason that we're interested in space exploration in the first place, of course, is to search for life. And life actually likes extreme environments, which is kind of counterintuitive. But when we're thinking about life's origins and microscopic life, which is what we think we'd be most likely to find on a planet like Mars in its geologic record, extreme environments are really good for prebiotic synthesis reactions, which is basically the original chemical reactions that allowed biomolecules to form before life was actually around. So we think extreme environments were important for that on Earth. So we like looking at those places on Mars, and places like Death Valley help us do that.
That's awesome. It's a lot easier to get to, I imagine, as well.
Yeah, although I'm sure it's just as harsh as going to Mars, except there's still oxygen. So
tough things about the road trip through that area for sure. But a really amazing spot on Earth, but not the primary focus for your research, right? That's other folks focus on Death Valley?
Yep, that's not me.
So where should we head if we wanted to see a spot that you personally have checked out?
So next, I think we're going to head to the Pilbara Craton of Western Australia.
So talking about difficult trips, I imagine getting to Australia is also kind of a schlep, as it were.
Oh, man. Oh, yeah. And just the fact that it's on the other side of the world, longest flight of my life. And one of the most stressful ones, too, not going to lie to you.
Well, we have had to cheat a little bit and turn off nighttime here on planet Earth, which also gets rid of some of our atmospheric effect. So if it looks like Australia has no atmosphere, we want to remind people that is not, in fact, the case. There is air wrapped around Australia as well.
It's not that much of a Mars analog.
Okay, so Pilbara Craton, am I saying that right?
Yeah. Pilbara, same thing.
Well, I'm more worried about the Craton part. What is a Craton?
So a Craton is basically just a really big area of rock that is all around a similar age, and we study those rocks together. So there are a couple of big Cratons on Earth. Personally, I'm not sure if this is 100% right, but I personally associate the word Craton with Precambrian rock formations, which would be older than 540 million years. So the Pilbara Craton specifically, the rocks in it are between, I believe, 2.7 and 3.6 billion years old, which is why I personally find the Pilbara Craton so interesting, because similarly to Mars, the Pilbara Craton is in a relatively tectonically inert area, so it hasn't been super affected by crustal recycling or anything like that. So that's the reason that we have such old rocks in this area. And when we have rocks that are that old, we also have really old traces of life, which is what I am most interested in, is understanding how we look for life, where we look for life, and when we're looking for life, what are we looking for? So in the astrobiology business, we call those things biosignatures, which you can think of similarly to like a fossil, except instead of having something like a bone, you have something like a molecule or an isotopic signature, something like that. And one of the really cool things about the Pilbara Craton is that we have both chemical biosignatures and like actual microfossils. And when you combine those two things together, you can learn a lot about where life came from, what it looked like 3.7 billion years ago, which is just crazy to think about. And personally, one of my favorite types of fossils, and one of the types of fossils that I think is the most interesting, is something that's called a stromatolite.
I think we actually had a photo I'd love to show folks.
Mm-hmm.
So Mary asked, and I'm thinking the exact same thing. This kind of looks like Mars with the red rocks and green stuff. And are these actual colors, or is this somehow enhanced?
Oh, no, those are actual colors. Australia is very red. And one of the reasons for that is because these rocks are so old. So they're actually very iron rich because they were. I'll talk about this a little bit more when we get to the next, or one of the next locations where we're talking a little bit more about
lots of places to see.
Yeah, lots of places to see. But the really old rocks tend to have a lot more iron in them for reasons that we'll get into later, which is why it looks so red, because there's a lot of oxidation, which is very similar to the crust of Mars, actually. Yeah.
So let's pop up that first photo, because this is a fossil, but it's not like going to be a dinosaur bone or something like that. This kind of life wouldn't leave big fossils like that behind.
Nope. So if you can see there, so that's my finger for scale, but so you can see that this looks like a pretty much normal rock, but if you look closely, you can see that it has these sort of like wrinkly layers going through it. And as a Precambrian geologist, when you see that, that's like the most exciting thing in the world, because that means that this is actually a fossilized microbial mat. So this is like growing out of the seafloor, just layer upon layer, year upon year, kind of like how a tree ring forms, like rings inside of trees. And over time, these layers died and were fossilized. And we see a lot of these in the Precambrian rock record, but as we get closer towards the modern day, we really don't see them often anymore. But there are some locations on Earth, such as our next location, that we do actually see modern stromatolite formation.
So this is not too far away, still in Australia, kind of just a hop, skip, and a jump, planetary-wise, but I imagine it's got to be a pretty long drive.
Yeah, so I have actually done this drive, driven from Sharks Bay into the Pilbara Craton, and it takes like a couple of days to get between those two. But that's also with lots of stops because geologists always have to stop and look at rocks. So.
Okay, so we're driving down into Sharks Bay where we can see sort of a maybe modern ancestor of the fossils we saw before.
Yep. And there is some genetic difference between them, I'm sure. I'm not a biologist, so I couldn't really tell you much about it. But the way that the microbial mats in this location form, we think are very similar to the ways that they formed in the ancient rock record. So if you see those kind of like gray little dots, those are all stromatolites. And I think we also have a picture of them from eye view rather than from bird's eye view. Yeah, so you can see those little things popping out of the water column. Those are all stromatolites. And the reason why it's so cool to study areas like this is because in this Western Australian region, you have like a couple of hours of driving and you can see something forming in the modern day, and you can see it in the geologic record. So that gives us the ability to look at a living organism and really study how it becomes a fossil. And that's so important for understanding how we can look for life in non-Earth-based geologic records, because we're studying how something actually goes from being alive to being preserved in a rock.
That's fantastic. So not that we have, but were we to discover a rock like that first image we showed on Mars, it would be a pretty big day for many sciences here on planet Earth.
Oh yeah, and I mean, there's actually a lot of controversy in the stromatolite world. You wouldn't think it would be, you wouldn't think it would be a big beef all the time, but it is. There's a lot of controversy over whether or not things are actually stromatolites, because there are ways that you can form those just through compression of rock, and you can get like little laminae in there like that. And usually you can tell the difference, but that's why it's so important to have both like an actual fossil and also the ability to measure the chemistry of the rock. So you can look at things like the carbon isotopes, which could tell you if that's actually an organic material, or you can look at the elements that are present and stuff like that. So I guarantee that if we ever found a rock like that on Mars, the astrobiological community would be ripped asunder.
So we had a question from Corey. When we're not in pandemic rules, is this travel a big part of your research, it sounds like?
It is, actually, yeah. So the next location that we're going to is actually my primary field site. I do get to travel a lot to do my research, though, which is my absolute favorite thing about doing research.
So this is in Canada. We were not far from one of the Great Lakes.
Yes, so we're on the northern shore of Lake Superior. We're sliding into an area that is specifically known as Kakabika Falls. And I think I have an eye view picture of that one as well, if you want to pop that on the screen. Yeah, so that's what it looks like if you're actually standing there. Very beautiful. And Kakabika Falls is in southern Ontario, again, along the northern shore of Lake Superior. And it is in a region where there's a rock formation called the Gunflint Formation. Mm-hmm. And the Gunflint Formation is about 1.8 billion years old, and it's a type of rock called an iron formation, which is a lot more common in the ancient rock record than it is in the modern record. And now we can get back to talking about iron, like I promised I would. So
excellent.
So the reason that we see so much more iron in the ancient rock record is because iron exists in two different valence states. For anybody who's not familiar with that, that is a reduced form of iron, iron 2+, and an oxidized form of iron, iron 3+. And there are a lot of really important differences between those two valence states of iron. So in our modern atmosphere, our modern ocean, where we have lots of lovely oxygen, oxygen acts as what we call an oxidizer. So we have a lot more of the oxidized version of iron in the ocean, iron 3+. And iron 3+ is very insoluble. It doesn't like to stay in solution. It likes to bond with oxygen and form iron oxides, which is basically just rust. And it crashes out of the water, and those are the only iron minerals you really see. But in the Precambrian aeon, which is from about 4 something billion years ago, 3.8 billion years ago, to 540 million years ago, we have very little atmospheric oxygen. So atmospheric oxygen mostly came from the rise of photosynthetic organisms, and those didn't really start appearing in the fossil record until about 2.5 billion years ago, at which point we call that the Great Oxidation Event. And then between 2.5 billion years ago and 540 million years ago, the level of atmospheric oxygen was slowly rising until we got to our present atmospheric level. But banded iron formations are all forming during this time period where we don't have as much oxygen, so we can have a lot more iron dissolved in the ocean. So we can reach saturation with respect to a lot of different iron minerals, which ultimately results in precipitation of these iron formations. So do you have that picture?
If I could try and fire back then, the presence or absence of oxygen in the atmosphere changes how iron moves through the rest of the system and whether or not it shows up in rocks?
So you'll still see it in rocks, but it's just that the form will be different.
The form of it changes.
Yeah.
Okay. So the presence of plants then producing oxygen gives us this unique evidence.
Yeah, not just
plant-like structures.
Yeah. So in this period of time, we're actually looking more at like phytoplankton and photosynthetic microbes in the ocean. So next time you get a chance, thank a microbe for being able to leave.
I'll confess a degree of ignorance on what defines a plants versus them, but we could leave that for another show. Can you tell us about this image?
Yeah, so this is a picture of me in Karijini National Park in Australia. So this is an iron formation called the Hammersley Iron Formation. And I chose this one instead of showing a picture of the Gunflint because I think you can see the layers a lot better here. So you can see like around my head, there are like some of the darker looking layers and some of the lighter looking layers. So those darker looking layers are the more iron rich layers because they're more red and stuff like that. But yeah, you can just see the layering here is really cool.
Beautiful.
And that you get such nice layers like that means that it was formed on the seafloor rather than like in a shallower area of the ocean because you don't have a lot of perturbation from the waves. So you get these really nice tiny micro layers and they look really pretty. And then if you show the picture of the Gunflint rock that I sent you, you can see that this one, although I love it very much, it's just not as pretty.
A little bit less aesthetically pleasing, I would agree.
Yeah, but the Gunflint Formation is a really unique formation on Earth, in my opinion, because for multiple reasons, actually. So the Gunflint is one of the oldest rock formations that has microfossils, where pretty much everybody in the community generally agrees that they are indeed microfossils. Because again, like geobiologists and astrobiologists have a lot of trouble agreeing on what actually constitutes a microfossil or a biosignature. I always like to joke that if we found like an actual civilization of sentient beings on another planet, there would still be a group of astrobiologists arguing about how we could form that abiotically. So
that's pretty good.
It's honestly the truth. But so most people generally agree that the microfossils at the Gunflint are in fact microfossils. So it has some of the oldest traces of life on Earth. And also the Gunflint, compared to other rock formations that are a similar age, is very well preserved. And it has a relatively low peak metamorphic temperature. So most places the peak metamorphic temperature will be in like the 500s, something like that, 500 degrees Celsius. And the Gunflint is about 150 degrees Celsius as a peak metamorphic temperature. So most of what my research actually focuses on is how the chemical signatures of habitability can be preserved in the Gunflint and how we can interpret that to understand the climate and environmental conditions of the earliest marine organisms. Yeah.
Well, speaking of early rocks and their influence on marine organisms, I've taken us over to our next door neighbor planet, Mars, because I feel like we want to check out some of the places that humans have been exploring here and how that helps inform the story of your research.
Of course.
So I'm going to bring on, just for folks' information, some high-resolution photography of Mars, and it might make Mars look a little different than we're used to. So we're bringing on something called the CTX layer for us, and it's going to look like someone painted little thin stripes all over the Martian surface. I want to assure you that's not in fact the case. What we are seeing are high-resolution photos taken by an orbiting satellite. And since it flies past a good swath of Mars, we get good high-resolution images of a long strip across the surface. So we are seeing these strips tiled in here, but this is real. actual information taken from the surface of Mars that we are going to go visit. And we are specifically visiting a place, I believe, called Gusev Crater.
Yep, Gusev Crater.
Gusev Crater.
Mm-hmm. Yeah. So Gusev Crater was the landing site of the Spirit rover, which landed on Mars in 2004. And the reason that Gusev Crater was selected as a potential landing site is because from orbit, it looked like there were a lot of rivers funneling into it. And so scientists thought that it might have been the location of an ancient lake. That turned out to not necessarily be the case. We didn't find very strong evidence for that, although there is still some argument among the scientific community about whether or not there might be some lake deposits there. But what we did find that is maybe just as interesting is, firstly, Spirit found some deposits of silica, which on Earth we typically associate with a hydrothermal environment or like a hot spring environment. So again, that's a sort of extreme environment that we're looking for when we're thinking about prebiotic synthesis reactions. And then the other exciting thing that they found at Spirit is a group of rocks called the Comanche outcrop. And unfortunately, I couldn't find the coordinates of the Comanche, so I couldn't send it to you. But
it's somewhere in here. Just look very carefully.
It's somewhere. So the Comanche outcrop is exciting because it has a lot of a specific type of mineral called carbonate minerals. And I'm actually personally a carbonate geochemist. That's what I would consider myself. So I might be a bit biased in thinking that these are the most interesting rocks we could have found. But basically, carbonates are exciting for a couple of reasons. The first is that carbonates form from water. So we know that there must have been water here at some point in time because there are carbonates. Second, carbonates are really good at recording chemical markers of their depositional environment through stable isotope analysis. And third, carbonates are also pretty good at preserving biosignatures. So when we find carbonates on other planets, we get excited. Although the weird thing is that we actually think we should be finding more carbonates on Mars because the atmosphere is primarily carbon dioxide, and carbonates form when carbon dioxide from the atmosphere mixes into the ocean. It forms carbonic acid, which then dissociates into a bicarbonate ion, and then that bicarbonate ion forms carbonate minerals. But we don't see a lot of that happening on Mars, which is confusing.
So all the ingredients are there, but we're not seeing quite the amount of the reaction we would expect.
Yep, that's exactly it.
So I'm noticing that you pointed this out in our practice, and I think it's absolutely fascinating. If you look at the area around this, it's pretty flat. Mm-hmm. And this marks one of the earlier attempts by NASA to land a rover on the surface. Yep. I just want to encourage folks to pay attention to the topography as we go to our next site, because I think NASA got a little bit more ambitious as things went on.
Yeah, but they sure did.
So we got to head all the way to the other side of Mars in order to visit Gale Crater.
Mm-hmm. Yeah.
Okay, let me take us over there and give us a chance for our tiles to load up so we get a nice high-resolution view. Gale is our site for Curiosity.
Yep. So Curiosity has been kicking around Gale Crater since 2012.
So
and
long.
Not as long as the Opportunity rover, though. The Opportunity rover lasted for 15 years on the Martian surface, which is crazy.
We were joking about them being powered by Energizer because they just kept going. But it's actually the sun, which I suppose can beat Energizers.
Yeah, for some reason, who knows? But, yeah.
Okay, so here we are at Gale.
Mm-hmm.
I can pilot us around so we can see the central peak. That's Aeolus Mons to some people and Sharp to others. Yep.
I think technically it's Aeolus Mons, but colloquially it's Mount Sharp. But Mount Sharp is actually the primary reason that Gale Crater was selected as the landing site for the Curiosity, because basically that mountain right there is about 5 kilometers of layered sedimentary material. And sedimentary material is much better than igneous or metamorphic material for understanding a depositional environment and what that means about the climatic conditions in that environment. So Curiosity's main mission was to drive around this mountain and sample all of these different layers so we can get a nice, long duration record of climatic conditions in Gale Crater. And it found some really cool things, and this is one of my favorite Mars facts and a really good example of Mars tying back into Earth. So one of the things that Curiosity has found at the base of Aeolus Mons is these mudstones that were, we think, lake bed deposits. And when some scientists, including my dissertation research advisor, studied these, what they found was that there's this really abrupt juxtaposition between iron-rich mineral phases and silica-rich mineral phases. And from that, they did some geochemical modeling work to show that there was an ancient lake at Gale Crater, and this ancient lake is redox stratified, which basically means that the lake has like a top layer that's being exposed to the atmosphere. So you have oxidation of iron coming from trace amounts of oxygen in the atmosphere and from UV photons, which can also oxidize iron. And then you have the lower column of water in this lake that's being fed by groundwater fluids percolating through the Martian crust. And those are bringing all these dissolved ions with it. And those are below a certain line where oxidizers can touch them. So you have a stratification between oxidizing and reducing conditions. And the reason that I get so excited about this is because that is very, very similar to how we think banded iron formations formed. We think that the ancient ocean on Earth was redox stratified, and that the slow breakdown of that redox stratification is what brought us into modern ocean chemistry. So this is just one example of how we can study an Earth phenomenon from a Martian perspective, which I think is so cool.
That really is. So we're seeing on maybe not identical, but reminiscent process on Mars that could inscribe similar kind of layering in the Martian rocks from a process we recognize here on Earth.
I don't think you would get the same kind of layering because the Martian environment is just like, it changes less.
It's too inactive. That makes good sense.
Yeah, so you would see like similar minerals, but I don't think you would see similar layering. But it's still a similar process, which is awesome in and of itself.
So we're taking another big step back. You can see just how many of these photos have been spent on the area around Gale Crater and Mount Sharp. It's definitely an area of a lot of studying happening. Attention lavished upon it. But we are going to go visit a spot that is currently getting a lot of attention lavished on it because we are sending a spacecraft there, which is going to arrive very shortly.
February 18th.
Oh boy, put it on your calendars. Great Valentine's present from NASA. Okay, so we are heading to Jezero. Why Jezero?
So Jezero Crater was selected for a lot of reasons. One of those is that Jezero Crater is located within a structure that looks a lot like a river delta. And on Earth, river delta environments are really good at preserving organic material and transporting a lot of material from upstream down into the delta. So not only are we looking for that sort of organic material, we're also hopeful that having a lot of material transported to one place will give us a good view of more diverse areas. So, and then the other reason that Jezero Crater was selected is because it is one of the few spots on Mars where carbonates have been detected. So, and like I said, carbonates are really important when we're thinking about climatic studies and about searching for life and understanding the environment of ancient Mars, especially since one of the main missions of the Perseverance rover is to collect samples that will one day be returned to Earth. And when we can bring carbonate samples back to Earth, there's so much that we can do with them to understand more about this environment in this area. So like personally, the isotope systems that I work on can tell us about temperature, or they can tell us about pH. And other people work on isotope systems that can tell us about a ton of other chemical things. So once we can bring those samples back, we'll have a really awesome idea of what this place looked like billions of years ago.
So these samples that Perseverance is destined to return to planet Earth, scientific samples valuable beyond measure. If you, Ella, got to pick the sample that would be delivered to you personally, where would you collect from? Where would be the piece creme de la creme?
I would go to the marginal carbonates. So that's a carbonate deposit that's located within the inner crater rim. And the reason I think those carbonates are the most interesting ones is because that's the area where from orbit we've seen the most intense carbonate absorption peaks. So that's where there's a lot of carbonate and there's not that much igneous material, or not as much as there is in other places. And that's important because most of the carbonates in Jezero we think are alteration products. So we think they're the result of fluid alteration or hydrothermal precipitation from the impact of the crater. But we think it's possible that the marginal carbonates were actually deposited from an ancient lake. So we call those a lacustrine carbonate. And lacustrine carbonates are super valuable because that, rather than telling us about alteration, tells us about a primary environment.
So kind of like we're so excited to get the oldest rocks and really understand how they've subtly changed here on Earth. Mm-hmm. Getting these oldest rocks on Mars gives you that kind of frozen moment in time that might match the earliest missing rocks on planet Earth.
Exactly.
That is a wonderful, it's incredible to think going to another world to learn about the world you're on, but that is a really powerful idea. So yeah. I think we had one last image I really wanted to touch on because it's showing us some of the chemical abundances around Jezero. And as we are super excited about the upcoming Perseverance mission, we want all of you to be excited too. Ella, why is this such a cool photo?
So this photo was taken by XRISM, which is one of the instruments that's orbiting Mars right now. And what this shows is where the infrared spectra from XRISM have different absorptions. So basically what this is telling us is about the mineralogy of Jezero. I don't totally remember off the top of my head. I should have looked this up, what colors mean what. But basically we have some of these colors are a mineral called olivine, which is an igneous mineral. It is an iron or magnesium silicate. Some of these are carbonates. Some of these are clay minerals. And basically maps like this are what caused Jezero to be selected, because it has a ton of mineralogical diversity. And when we want to get as much information as possible about a location, mineralogical diversity is what we want.
So this is maybe going to give us the most information about the most kinds of rocks.
Yes, definitely.
Fantastic. Well, thank you so much for joining us here. It's been an absolute hoot. And I think I really want to hold on to that idea of what we can learn about our own place from visiting other places. I think that's something really special. Thanks. So anything else you'd like to share with our audience?
I don't think I have anything else. If anybody has any questions, I'm happy to answer them. But
we have been addressing along the way. I'm going to open it up in case anyone else has something else to drop in. But for you, what would be an incredibly exciting discovery? What would be something that would set your research group spinning for a find on Mars?
So something I haven't talked about a lot today is phosphorus. And phosphorus is one of the most interesting elements to me personally, because it's so important for all life processes, but we have no idea how it became that way, because phosphorus on Earth really wasn't super abundant. And it still isn't super abundant because most of the bioavailable phosphorus gets tied up in phosphate minerals because we have so much calcium. And that's not the case on Mars. So there have been some studies that suggest that phosphate could have concentrated way higher on Mars than it did here, which would be so important for early synthesis reactions. I can't even begin to express it. So the most exciting thing that I think we could find would be if we find really high levels of phosphorus at Gale Crater. I think that is the dead ringer for me personally.
Fantastic. Well, I hope we can all stay tuned and keep following along. If you are interested in Jezero, Perseverance, and upcoming Mars stuff, I would encourage folks to stay tuned to both OpenSpace and the Morrison Planetarium Facebook page. We are always keen to share out whatever we learn. We even have an opportunity to interact with some of our NASA astronauts on February 17th. So, Ella, from all of us at Morrison and OpenSpace, thank you so much for joining us. This was an absolutely fantastic conversation.
Yeah, thanks so much for having me. I had a great time.
And for everybody, thank you all for tuning in and joining us here while we are broadcasting from our homes to yours. Please enjoy the rest of your Friday, and we hope to see you again soon. Have a great day.